Well, good morning, grade 11s. Yeah, I've got another lesson for you. And before I start this, I just wanted to point something out. Um, yeah, if you want extra help from me, and like let's say I've given you a lot of work, which I have. I've given you a couple of assignment sheets, and I've given you some textbook homework. Um, you don't have to wait for us to do a group chat all together for you to ask questions. You can either email me a question, you can send me a question, whatever format you want to send it in, whether it's on the Snapchat or whether it's on email, I don't really care. That's up to you. Or if you want to have a live conversation and, you want me to be writing the solutions, on the board or on the screen while we're talking about it. I did that last night with a few of your classmates and it worked really well. So you don't have to wait for all of us to do it together. Maybe with 30 people doing it together, you don't get enough attention that way. So if you have a lot of questions, okay, then maybe you could just organize a time with me and I could do it live with you. And I've got lots of time on my hands, so I don't mind doing that at all. So yeah, keep that in mind. All right, so today's lesson's kind of short. It's on, believe it or not, bathroom scales. Okay, now there's maybe one or two questions about this somewhere in the homework, whether it's on the worksheet or not, but usually on a quiz or a test, I ask a question like this. So you know what a scale is. You stand on it, and it tells you, well, what does it tell you, right? It tells you, in this case, this woman, it says 114.3 pounds. Now, what does that number mean? Well, it's her mass, okay, in this case. So mass is how much matter is in your body, okay? It's the amount of matter in your body. That's your mass. Now in Canada, let's say we use the metric system, so that's measured in kilograms. So that's the standard international unit of mass is kilograms. This is about 2.2 pounds in a kilogram, right? So this woman, you divide that, she'd be somewhere around 2 kilograms, something like that, okay? 52, I don't know if I'm doing the math right in my head, but somewhere in the 50s, okay? She's 114.3 pounds. So just roughly divide that number by 2, okay, to get kilograms. All right, but a scale reports your mass, but how does it measure your mass? Well, you stand on it, and what it does is it measures the force of contact between you and it, okay? So in other words, what it's really measuring is a normal force. It's measuring like how much contact there is between the surface of the scale and your foot. And based on that number, it just takes that number, which is a force measured in newtons, okay, divides it by 9.8, because usually the normal force is equal to the force of gravity. So if you take that force of contact and divide it by 9.8, it should tell you what your mass is. Okay, so I'm going to remind you of a couple of things. Okay, I'm going to draw a little diagram here in the margin. So let's say you're standing on a scale. So here, this is a system diagram. This is you. This is your scale, and this is the floor. Okay, so here, I'll make, there, that's you. Okay, you're happy because it's a physics lesson, so you must be very happy to be listening to this right now. Okay, here's your scale. Okay, that thing on the floor you're standing on. Now, what does the scale read? Like I said, what it measures is normal force. So how much contact there is between you and the scale. Okay, so your free body diagram will look something like this. This is you. Okay, so your free body diagram, gravity, yes, it's always there. And the only other thing is this normal force. Now this normal force is the contact force on the scale. And that is the scale, right? So what the scale does, it measures Fn. It measures that force of contact. Okay, but it doesn't give you an answer in newtons. It could, but it doesn't, because we don't want to know like your force of gravity on your body, like, the amount of contact. We want to know how much mass you have, right? Now, in this diagram, if A equals 0 in this diagram, then what does that mean? Well, the net force is equal to Fn minus Fg. I'm choosing up as positive. It really doesn't matter since there's no acceleration. So Ma equals Fn, and of course gravity is mg, right? Where g is always 9.8 meters per second squared. Now don't get confused. They're not accelerating at 9.8. It's just that's how we calculate the force of gravity on your body, right? So this person is not accelerating at all, but this is their weight here. See, and don't get confused. That is weight. Remember, weight and mass are not the same things. Weight is the force of gravity on your body, and your mass is how much matter is in your body. Okay? So, in order to do this one's 0 because the acceleration is 0, and therefore Fn is just equal to mg. So, the scale, okay, what the scale does is the scale measures this number, okay? So it measures this number here. And then to get your mass, what the scale does, so again, I'll talk about the scale. It measures Fn, okay, and divides by g. Okay, now when it does that, okay, if I just go here, m is equal to Fn divided by g, right? If you just take that equation and solve it. So that's equal to your mass. Okay, so if that makes sense to you, that's what a scale does, is it reports your mass by measuring the normal force and dividing by 9.8. Then it can then calculate your mass, and that's how it does it. Okay, so you stand on it, it reads the normal force, divides by mass. Now you can fool the scale, okay? And how would I fool the scale reading? Well, let's say I were to, like if you're standing there, let's say someone, okay, were to come up behind you and push your shoulders down, okay? So in other words, they didn't increase your mass, but what they did was they increased the normal force that's on your body because you're now being pressed into the floor or into the scale more. I think you know that that would increase the reading, right? Now you haven't really increased your mass, but what you've done is you've increased the normal force. Gravity has stayed the same, but you increase the normal force by somebody pressing down on you, okay? And the scale will read incorrectly then, it'll say a higher number. Now, what if we were to lift you a little off the scale, like someone was coming and just lift you up by the elbows or something, right? And then what happens is that would decrease the amount of contact between you and the scale. And that, again, would give a false reading. You would have less, it would look like you had less mass. But of course, your mass didn't change. If someone is like sitting on your shoulders or someone is lifting you up, that doesn't change your mass. But what it does is it changes the amount of contact between you and the floor. Okay? And so that's important. Okay, now that you know scales and you know how they work, okay, let me show you an example of what happens when you're standing on a scale, okay, in an elevator. Okay, now I've got this video here. It was working before, so let's see if it works now. Okay, I'm going to skip. So this guy goes in an elevator, long story short. He goes in an elevator, he presses on the button. Now his weight is 120 pounds, okay? He presses up in the elevator, okay, and it says here, what will happen when, in England, they call an elevator a lift, okay? What happens when it goes up? Okay, explain your prediction, so on and so on. We're not going to do all this. But what do you think is going to happen to the reading on that scale? He's standing on the, like an elevator's kind of special, right? So he's standing on the elevator. What will happen to the reading on the scale? Now watch, he's 122, and did you see that? I'm going to pause it there for a second. If you look at that, the reading, he's 122 pounds. Okay, and when it starts accelerating up, the reading, oh, hang on. So it increased right there to 130 pounds, it looks like. You know what, I'm reading this scale wrong. I'm realizing these are worth 2 each. So he's around 126 pounds. It increases to 130 pounds. Now all he did was go up in the elevator. Now, as he continues to go up, it quickly goes back down to 124 or whatever that reading is. Okay, each tick is worth 2. So that's his normal mass. His normal mass is 124 pounds. Okay, now that I'm reading it right. And that went up to 130. So it looked like he gained 6 pounds. And all he did was go up in the elevator. Now he's still going up here. Okay, he's still going up, but the elevator accelerates at first upwards, and then it maintains a constant velocity going up. And once it maintains a constant velocity, the scale goes back to normal. Okay, that's going up in the elevator. So the number increased when he went up. Now, what about if he goes down? I'm just going to find that spot where he's going down. So when he goes down in the elevator, what do you think is going to happen? So here's his normal weight, right? So now he's going to go down. And now, you see that? So he's accelerating downwards. And when he accelerates downwards, it used to be 124. Now he's down to 118 pounds. Okay? So the reading went from 124 to 118 pounds. That's the elevator accelerating downwards. Now, if you watch, it goes back to his normal weight. Now he's still going down at this moment. Still going down. But while it's going down at a constant velocity, it reads his weight normally again. Okay? And actually, if you look there at the bottom, what's happening there when it just shot up to 130 is the elevator stopped. And when it stopped, it's a deceleration and the reading increased. Okay? So it's going down but slowed down. That means you're moving down but accelerating up. And the reading increased again, okay, when it stopped. So what's going on in this elevator? If you want to try this, you know, the best elevator in the city to try it, okay, you got to wait till after this this sort of voluntary quarantine time is over. But take a bathroom scale, go to the Westin Hotel, okay, in the Rideau Center. Those elevators have amazing acceleration, okay, and there's a couple of fun experiments you can do there. If you don't want to bring the scale because you think that's weird, then go in the elevator, press up, and just as the elevator starts to move, jump in the air. Okay? And then just trust me, it's a fun experiment. We did it when we were kids here. And when the elevator is going down, do it again. Okay? And you get a lot of hang time when that thing accelerates down. It's a kind of a fun ride. All right, so what's going on in the elevator? So I'm going to explain this. Why does the scale read incorrectly? Okay, so the elevator problem. The lesson today is about the elevator problem, just one kind of problem. Okay, so how does that work? Well, here, let me draw the system diagram. This is the elevator. This is you. This is, here, actually, can I fix you? This is the scale. And this is you. Okay? And let's say in this example, the elevator is accelerating up. Okay? And let's say it's accelerating up at, I don't know, let's give it 3 meters per second squared. That would be a very large acceleration for an elevator, but let's make it fun. Okay? This one's got a large acceleration. Let's say the person's mass is actually 50 kilograms. But what will the scale say your mass is? What will the scale reading be? Okay? Will the scale report a correct 50 kilograms? Okay? Actually, it won't. Okay? And what happens is, if you draw the free body diagram, you'll see why. Okay? So again, let's draw the free body diagram of the student in the elevator doing this weird experiment. I highly recommend doing this experiment. It's a lot of fun. So there's only 2 forces acting on that student. Okay, nothing else is touching them, right? Just the floor and gravity, of course, right? Now, the deal is, though, is that when you're standing in the elevator, you're going to accelerate up the same as the elevator, of course, right? If it goes up, you go up. That's the whole point, okay? So that's your free body diagram. Now, the fact that this acceleration is not 0 makes all the difference in the reading on the scale. Because if you go back up to our example here, it's standing on a scale on just in your house, well, the acceleration is 0. But the elevator's acceleration is not 0, and that's what causes the false reading, okay? But we don't want to just know why there's a false reading. We don't know what that reading is, okay? So watch. The false reading, if you want to, we need to find the normal force, okay? This is what we're really looking for, because the scale reads the normal force, right? So what we do is we go like this. The net force is equal to the normal force minus the force of gravity, okay? So ma equals Fn minus mg. We know all the numbers. We know the mass is 50. So I'm going to solve this for the normal force. So Fn will equal ma plus mg. Okay. Now that's 50 times 3 plus 50 times 9.8. Now if I take out my calculator, I'll just do it separately here. So 50 times 3 plus 50 times 9.8 is 640 newtons. Now, the scale doesn't report in newtons, right? So the scale reading, remember how scales work. The scale reading will take the normal force and divide it by 9.8. See, the scale is assuming that the only force is acting on your body, your scale is assuming that this is the force of your contact. So it divides by 9.8, it should get 50. But you're going to see we won't get 50 this time. What's going to happen is we're going to get 640 divided by 9.8, okay? 640 divided by 9.8, that is 65 kilograms. That's actually 65.3 kilograms. So remember, this person doesn't weigh 65.3 kilograms. They weigh 50. That hasn't changed. But the scale is saying that you now weigh 65.3 kilograms when you're accelerating up like this, okay? And isn't that funny, right? Like it's the wrong reading, and that is significant. A gain of 15 kilograms, that's like gaining 30 pounds. Like you're gonna feel that. See, it's not just that the scale reads that. This is the coolest thing. The scale doesn't just read that you're 65.3 kilograms. You feel like you're 65.3 kilograms too. You feel heavier when the elevator is going up. You will feel heavier, okay? I always tell students, like, you know, you can do this experiment. They have these things that they're not elevators, but they spin people around and give them acceleration. Okay, and they're for astronauts in training, and I could show you a video of that. What would it be like if you had this tremendous acceleration on your body? Like, what if we had that elevator accelerating up at like 100 meters per second squared? What would that feel like? Okay, well, if it was 100 meters per second, here, let me just put it like this. What if A was equal to 100 meters per second squared? Okay, then what would the scale read? Well, let's just skip to this step here. We know that the normal force would equal, instead of 50 times 3, it'd be 50 times 100, okay, plus 50 times 9.8, right? So that's 5,000 plus, yeah, I'll just do it. 50 times 100 plus 50 times 9.8. 5,490 newtons. Now the scale will tell you this. I'm going to divide that by 9.8. The scale will say that you weigh 560 kilograms. Now, in case you're wondering, because this unit of kilograms may be not as familiar with you with scales, I want to convert that to pounds. That is 1,232 pounds. Okay? That's how you write pounds, LBS, for reasons I'll never understand. But anyway, yeah, 1,000 pounds. Okay, here's the thing. If that elevator was accelerating up at 100 meters per second squared, how many of you could lift 1,000 pounds with your legs? Okay, like probably none of you. I can't do it. That would break my legs. Okay, 1,000 pounds. That'd be like lifting a smart car, right? You'd weigh as much as a small car. And here's the thing, it's not just that the scale would read that. You probably crushed the scale, first of all, but the thing is that's how you would feel. You would feel that heavy, okay? And that's how scales work. Like that's how the elevator works. When you're in this accelerating frame, the amount of acceleration is really important. In fact, you could not survive this. Like if you can imagine a scenario where it would actually cause your body to be crushed, okay, by basically your own inertia will crush you. So if you weighed that much, look out, you're going to get crushed, okay? And we could increase it even more. What if it was 1,000 meters per second squared? Well, you're toast. You're finished. Your legs will break. They'll snap, okay? And in fact, they do experiments where guys are being spun around and they get up to around, I don't know, maybe about 70 or 80 meters per second squared of acceleration, okay? And the stress on their body is so insane, okay? I'm going to show you a video just because I'm mentioning it. I want you to see it because it's kind of cool. So just let me find it for you. Okay, give me a moment. You won't see what I'm doing, but okay. Okay. So what does it look like when guys are experiencing this huge rate of acceleration? So I'm gonna put a video here. Pardon me if it makes a noise. Okay, so let's see if I can get it. Control C. Put this video in here. Okay, I just want to say before I put the video, actually I'll put the video right here. Control V. Here's the thing. Okay. It's not just that the scale is reading this. You actually would feel that heavy. Like you would not be able to stand up, okay? Now these guys are sitting down, strapped in. They have to be, and they're not accelerating upwards so that their spine doesn't get this tremendous stress on it. They're kind of accelerating forward and being pushed back in their chair, like the equivalent of you lying down in the elevator, okay? So in fact, astronauts, when they're taking off into space, they have to be facing the direction they're going. It's kind of in the lying down position, okay? All right, so here's this video of guys accelerating. I hope this works. Let's see. All right, now I'm not going to show you the whole thing. I am just going to skip to this guy here is very funny. Okay, so take a look. Watch, see his face. Now he's going to accelerate. Right there he's accelerating. Look at the distortion. His face is so heavy. Okay, now watch. He'll pass out. Okay, he's pretty much passing out because the blood is rushing away from his head under the strain. Okay, so his eyes roll back, right? And you can see the number of G's of acceleration, so multiply that by 9.8. There's a funny guy too that this guy here. Okay, now pilots have to train this way. So now he's actually like, okay, wait, here, let me rewind that a little. Okay, so here at the top of the screen, you can see the number of G's. So he's at 5 G's, that guy. He's already passing out. Okay, watch this guy. Here they increase it, 7 G's. So 7 times 9.8, that's about 60 meters per second squared. And he is out, that guy. Okay. But here's the thing, his body would feel that heavy. He would not be able to even lift his arm. Okay, now they've put it back to normal. But yeah, he's just... Anyway, it's a very entertaining video to watch. and then they come back. What happens is your brain loses oxygen briefly, and they pass out, and then the guy operating the machine will quickly dial it back. These are pilots in training, okay, fighter pilots. Okay, so here's the deal. That's an elevator accelerating up, and why the scale reads incorrectly. Okay, now what about if it was accelerating down? Well, we saw in this video here, okay, that the reading decreased. It went to about 118 pounds. So why did that happen? Well, okay, well, let's do that. Let's say you're going here. Actually, let's say you're accelerating down instead of up. Okay, and we'll keep it. We'll keep this number reasonable here. We'll go 3 meters per second squared, which for an elevator, right? Actually, wait. Let's just go straight to the free body diagram. So the free body diagram of the guy, the student, there's gravity, there's a normal force, and A equals 3 meters per second squared, this time downwards. And again, we need to find the normal force. The guy's mass is still 50 kilograms. It's the same person. Now he's just going down, okay? All right, so this time, the only difference this time is because the acceleration is down, we have to pick down as the positive direction and not up. So the net force, if down is positive, is the force of gravity minus the normal force. See the difference, right? When up is positive, it was the other way around. It was the normal force minus the force of gravity. But now, because down is positive, we have to switch these two things and make gravity the positive force and the normal force the negative direction, right? So I get ma equals mg minus fn. Now I have to solve for fn, so I'm going to bring the normal force to the other side, bring this to that side, and I end up getting that fn, just doing the algebra quickly, is mg minus ma, okay? And that's equal to 50 times 9.8 minus 50 times 3, okay? So what is that? Let's try it. 50 times 9.8 minus 50 times 3, 340. So that's 340 newtons. But again, the scale will divide that by 9.8. 34.7 kilograms is the scale reading. Again, he's 50, right? He's not 34.7, so he's feels a lot lighter now. So if you're wondering what that is in pounds, divided by 2.2, that is 15.8 pounds. 15 pounds. The guy weighs 100 pounds. Okay? Like he weighs, wait, did I do that right? 34.7 times 2.2, pardon me, no, I didn't do that right. 76 pounds, yeah, that's better. 76.3 pounds. Anyway, the guy weighs over 100 pounds, okay? But now he feels like he's just 76.3 pounds. So you want to lose weight? Go in an elevator, right? Accelerate downwards. But of course, your mass hasn't changed at all. You're still you. You haven't lost any matter in your body. But the scale says you're lighter, okay? So when you're on the way down, the scale reads less than it should. And it kind of makes sense. You kind of are losing a little bit of contact with the floor as you accelerate downwards. And you'll actually feel lighter. Now, is there a scenario where the scale would read 0? And the answer is yes. Okay, and I'll just do this on the margin. What if A is 9.8 meters per second squared? Well, that happens to be the acceleration due to gravity, right? So if A was equal to 9.8 meters per second squared, you're in free fall. That's like they cut the cord, you're falling, and the box that you're standing on, like the scale that you're standing on, is falling too. So if that's the case, let's just skip to this line here. The normal force then would equal 50 times 9.8 minus 50 times 9.8. Well, that's 0. And therefore, the scale reads 0 kilograms okay, and you feel weightless, okay? And isn't that bizarre? You would feel weightless. So if you've ever taken a ride on, I mean, I can think of a ride where they drop you. Yeah, actually, did I show you this already? Yeah, I thought I showed you this, but anyway. Oh, no, okay, yeah. So there's a ride you can take. That was my grade, I'm getting confused with my other class. My grade 9s, I showed them this already. Okay, not the physics, but here. I'm just gonna show you a picture. Okay, so there is a ride at Canada's Wonderland. And I'm just going to show you a picture of that ride right now. I'm going to put it in the notes. So there's a ride at Canada's Wonderland that actually is an elevator. This elevator, okay, physically drops you. Like it actually drops you. Now if you zoom in, you can see the people here getting on at the bottom down here like that. Okay, and then they go up to the top of this 10-story tower. And at the top, they kind of play with you a little. They'll say, all right, we're going to drop you on the count of 5. 5, 4, and then they drop you, right? And the idea is to surprise you. But you actually get a ride to the top. It's 10 stories up, and then you just accelerate down at 9.8 meters per second squared. And while you're accelerating down, you will feel weightless, okay? And I just wanted to point out to you another picture, and I'll show you like this. It's so weird not being together. I could just say these things and show you these things. It would be much quicker, but anyway. Okay, so I'm just going to find another picture for you. Okay, so here, let me find a good one. This is a good one. No, it's not a good one. Okay, this one here. Yeah, that was pretty good. All right. So this picture here is astronauts on the space station, and they are floating, okay? Now, are they floating because there's no gravity in space? False. They're not floating because there's no gravity. They're floating because they're weightless. Now, they're basically in a box, and that box is accelerating all the time. It's in free fall. So in other words, their box, the ship that they're on, if you want to think of it like this, here's Earth, okay? And here's their ship, not to scale, okay? And it's whatever, it's orbiting the planet. But the thing is it's like a projectile. Its acceleration is always down, okay? Now it's moving this way, but accelerating downwards, that's a property of what we call circular motion or whatever, centripetal motion, okay, that we learn about in grade 12, but they're in free fall. So these guys are in free fall all the time. And we just did an example, this example here, if the elevator was in free fall, how would you feel? You would feel weightless. You would lose contact with the floor altogether. And you could float around in your box. Now, of course, if you're in an elevator, you're in great danger because if you cut the cord and you're in free fall, you're going to crash in the bottom. But these guys never crash because they're not actually falling straight down. They're falling on this arced path. So they never actually get closer to the Earth. But they're in free fall all the time. So there's gravity out there. They're not so far away that their ship wouldn't experience gravity. In fact, gravity holds the ship in orbit. So of course there's gravity there. But the reason why they're weightless is because they're in a falling box. Okay? And that's why they feel weightless. So there you go. That's how you do elevator problems. And The video took a long time because I had a few cool things to show you. So I hope you enjoyed this. There's a couple of questions like that, I think, from the homework or the assignment. And that will take care of the lesson for today. All right, have a good day, guys. We'll talk to you soon.